So last class we were dealing with some induction questions. This class I'm going to do a bit more writing. When I read something to you and give you the definitions, if you don't understand, then I'll explain it. If you understand, then I'll just move on. Because we need to get through functions and relations, and then we can start applying the different real analysis methods. All right, so here's a definition that you guys need to know. What number? First definition. I'll call it number 1 definition. All right, so
Sorry, topic?
Yeah, functions. Functions. You know, I bet Laffer and hear me just the one talk. I bet enough watch. All right, so all right, let me just read it to you and then so write this down. Let A and B be sets. Tell A and B. So let A and B be sets. Full stop. The Cartesian product. Hope you guys notice what Cartesian. You'd have seen it before in math. So the Cartesian product is the set of tuples that you might not have heard before. I'm going to tell you what that means soon. The set of tuples defined as A times B. The set of tuples, which is defined as A times B, which is this set here. X, Y, the pair X, Y, such that X is in A and Y is in B. What do you want me to repeat the definition?
Yes, sir. Everything that you said.
You can repeat everything we said. I said a whole heap of stuff before you told me that the mic is not muted. I'll just repeat the definition. Hopefully that's what you mean. All right. Let A and B be sets. The Cartesian product is the set of tuples defined as, well, nothing on the board. A times B, which is a set XY, such that X is in A and Y is in B. Yes. So does anyone know what a tuple is? It's a funny word right here. Ever seen it before? You know what it is? Remember how I work, you know? If you don't answer, that means yes. And let's move on. So does anyone know what tuple is? No. All right. A tuple is almost like I said, really, because some people say it's a collection of objects, but I think the best way to put it in mathematics is it is a set, sorry, it's a finite sequence or finite ordered list. Let me make a note of that. I'm going to give an example. You can have 2 tuples, 3 tuples, 4 tuples, and so forth. So it's like it's a finite ordered list. So like a 2 tuple, it's something you've seen before. You probably just didn't know that people call it that. It's something like this. 1, 2, or 3, 4, 3, 3, whatever. That's a 2 tuple. You could have a 3 tuple. which would have 4 of them. Sorry, 3 of them each. 3 tuple. And you have A, B, C. It's not a set, you know. It's just a list of stuff in the set. So like you could have two tuple where the set, this could be a set of 2 tuples. See, it has 1, 2, 1, and 3, 4. Was that two tuples, two tuples in the set. Like a 3 tuple has 3 elements in the set and so forth. So that's what a tuple is. A fancy name for something simple. I think name is probably complicated. All right. Next definition. Oh, by the way, let me just make sure you understand what they mean right here when they say A times B. It's important. So let's say in one set A, we have, let's say 1, 3. And in the next set B, we just have this. This is one member in the set, you know. It could be many more, but I'm just showing you how the multiplication goes. In one set B, we could have, let's say, 2 different numbers, 4, 5. Then if we were to multiply the 1, 3 and the 4, 5, like A times B, if we were to multiply 1, 3 and 4, 5 using the Cartesian product, you get the, as done a while ago, you get the set of tuples where X is in A and Y is in B. All right, that's A times B. So you could get something like this. You could get, well, you would get, not could get, you would get 1, 4, 1, 5, and 3, 4, 3, 5. So that's how you would multiply. Notice the definition said it's A times B, where you get XY, where X is from the A and Y is from the B. So you combine all the possible first numbers from X. So you see 1 is the first one in X and 3. So all the first terms must be from A and all the second terms must be from B. If you look back at the definition, when you multiply A by B, that's a B, you get the set XY, where the X, such that, the thing I wrote before, X is from A and Y is from B. In other words, the first element must have been from the A, the one at the front, and the second element comes from the B. Any questions about that? We understand that? No question. All right. Next definition. Oh, let me write something on the board and then I'll tell you how you will hear me read it from now on. So when I'm going to read this, I'm going to say it like this. The function f mapping A to B. So I'm going to expect it to write the words each time. So you can write it this time so you know that's what I'm saying. So whenever you hear me reading that thing in the box, I'm going to read it. The function f mapping A to B. So if I say the function x mapping P to Y, it would look like this. Function x mapping P to Y. That's an arrow. It's going to look like that. All right. So next definition now. We're actually defining function mathematically. All right, so here goes. A function f mapping A to B. A function, write the word this time. So write A and function. Then you write that thing in the box. So a function f in A to B is a subset f is a subset, common f, A times B, I'm going to write the words now, such that for each x in A, such that for each x in A, there is a unique pair xy in F, such that for each x in A, there is a unique, at the bottom of the board now, xy F. All right. So let's write everything on the board as I go along. Say it again. So a function f mapping A to B. Each time I'm going to write whatever is on the board that's not supposed to be written in the words, I'm going to write on the board. So a function f mapping A to B is a subset f of A times B such that for each x in A, there is a unique pair xy in F. Full stop. This is written f of x equal y. The full stop. This is written f of x equal y. So as you can see, it is a mapping from the x to the y. So this is something you already know. You're going to need this proper definition when you're doing the proofs. So you have to know exactly what the function is. All right. Sometimes you'll also see, write this as well. Sometimes the set f is called the graph of the function. Sometimes the set f is called the graph of the function. All right, next. So let's continue the definition of the function here. The set A, so using the same information as given a while ago, the set A, capital A, is called the domain of F. The set A is called the domain of F. Does anyone know what the set B is called? You're going to give me the wrong answer first, but try still. What do you think the set B is called?
Range.
I told you, give me the wrong answer first. All right, but the range is in B, but B is not the range. So write this down. The set B is called the codomain of F. The set B is called the codomain of F. So codomain is normally written with a little hyphen after the co and then domain. But although if you write them 12 together, people don't complete. At least not but from what I've seen. Now write this one down now. Not I want to tell what the range is. The set R of F, this is normal, it's normally written. The set R of F, so I write the word, the set R of F equal y in B such that, I can't write this word now, so you're going to write these words. So the set R of F equal the set y in B such that there exists an X, that's what you should have after the such that. there exists an X, blah, 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 an X such that, I run out of space. Why my X look ugly? There exists an X such that f of X equal Y. And you close the set. So let me read it one more time to make sure there's no confusion. The set R of F equal, the open set bracket there, Y in B such that there exists an X such that f of X equal Y. When you close it right there, you're going to write is called the range of F. In other words, what I simply said a while ago is the set R of F is called the range of F. But in the brackets there, you know what the set R of F is. So let me spend some time on this part right here. The big set B is called the codomain. And from that set, you can get the range. What we know, is that the domain maps into set B. But not everything in set B has to be a part of the range. It's possible that it is the same set. I mean, it's a range. Everything in there is in the range, but not everything has to be in the range. I'm going to give an example soon. Or maybe I should give it from right now. I'm going to give an example from right now. So you know what I mean. All right. Clear this board right here. So I'm going to show you from now what the difference is between domain and range. Oh, you know what? Write this first, so you can see exactly what I'm talking about. Write this along with what you just mentioned, what you just had a while ago about the range. It is possible that the range R of F. It is possible that the range R of F is a proper subset of B. It is possible that the range R of F is a proper subset of B. While the domain of F is always equal to A. While the domain of F is always equal to A. So just let me make sure that this is clear. What does it mean when it says that R of F is a proper subset of B? If I say that R of F is a proper subset of B, what does that mean? I told you before what proper subset means. So if I say that R of F is a proper subset of B, well, actually means not equal to B. A proper subset means that you're not equal to the set. So if A is the same set, this is an example now. Maybe use a different letter. So you don't think it's the same A and B. If X, the set X is the same as the set Z, then X is not a proper subset of Z. It's just a subset of Z. So for you to be a proper subset, you have to have this condition. For example, P is not the same as the set Q, but P is in Q. Then you would say that P is a proper subset of Q. So remember, to be a proper subset, you have to not be equal to the set. So no set is a proper subset itself, whereas every set is a subset of itself, but it's not a proper subset. Because to be a proper subset, you have to be not equal to the set. So for A to be a proper subset of B, then A cannot be equal to B. So what they're saying right there is that it is possible that the range is a proper subset of B, meaning the range is not necessarily equal to B. As I was telling you before. So I'm going to show you now how that happens and why one is called codomain and one is called range. So I'm going to use something that you guys are used to. Let's say we have this domain over here. Let's say the domain is 1, 2, 3. I'm sure you guys have seen stuff like this all the time. All right, since you have space, put a 4. And the codomain is this set here. Let's say it has A, B, C, D, E. Let's say 1 maps to A, 2 maps to B, 3 maps to E, and 4 maps to D. Just for argument's sake. What would be the domain? What would be the elements in the domain?
Four maps to what? C or D?
D. Oh, Anthony's here. Welcome, Anthony. Wait, Anthony, you been hearing me all along and not saying anything?
No, sir. I went to the bathroom, so sorry, I took a little while.
Oh, okay, all right.
Says A, B, D, E.
Correct. That's it. That's the But I asked for the domain, you know.
The domain?
Yeah, for this relationship here, for this function. What's the domain?
Oh, domain and range. Okay, the domain will be 1, 2, 3, 4.
Correct. So the domain will be where the mapping is coming from. 1, 2, 3, and 4. That is the domain. What is the range?
What I called before.
Where this again? Remember?
A, B, D, E.
A, B, D, E. Correct. So the range is the elements that are being mapped to, which is A, B, D, E. But the codomain is the entire set B. And as you can see, that codomain contains a C as well. So the codomain would be A, B, C, D, and E. So there is a difference between codomain and range. So the codomain is the set that has been mapped to, whereas the range is the actual elements in the set that are mapped to. We are mapped to A, B, D, and E. We didn't map it to C. So there's nothing from A going to C, even though the C is part of the next set that the elements are coming to, are being mapped to. So that's the difference between codomain and range. Everybody okay with that?
Yes, sir.
All right. All right. So moving right along. So even though you didn't mention that you didn't understand, I figured that some people have a little difficulty with that. So that's why I went through it. It wasn't mentioned before. As a matter of fact, I didn't learn that until when? The first year in university. I didn't learn it in high school. They always tell me codomain and range were the same thing. So I thought I'd mention it here. All right, next definition. I don't think you guys are writing anything, but if you are, let me know. No, all right, so next definition. Let f let the function f be a mapping from A to B. What I mean is this. I don't even know how to say it without saying the function. So let the function f be a mapping from A to B. That's this little box I write right here. So let the function f be a mapping from A to B. Be a function. Oh, I think I know how to say it now. Let f mapping A to B. Yes, that's how I'm going to start saying it. So let f mapping A to B be a function. What I said a while ago sounded redundant. So let me say one more time. Let f mapping A to B be a function, and C is a subset of A. I'm going to clear the board here. Full stop. The image or direct image of C, the image or direct image, if you prefer direct image, of C is defined as f of C such that f of x is in B. And of course, X is in C. Oh boy. All right, so I'm reading it again. The image or direct image of C is defined as that thing on the board. F of C is supposed to be capital C's. If it looks common in bracket, it's a mistake. Oh, when we're talking about sets, it's always capital. So the image or direct image of C is defined as F of C. Oh, I made a mistake here. Equal. I know I said such that. Confused myself. It's defined as F of C, which is equal to the set F of X in B, such that X was in C. All right. No. We're going to now define inverse image. So image, whenever you say image or direct image, it means you're going from the domain to the codomain. But if you're defining the inverse image now, here's what it says. So let D be a subset of C, of B, beg pardon. Let D be a subset of B.
Sir,
Uh-huh.
could you repeat direct image, what it means?
The direct image is the result of mapping from the domain to the codomain. So the direct image is the result that you get in the domain, in the range, beg pardon. You follow me? The direct image or image is the result obtained from the range. Get that? Michaela?
Yes, sir.
Okay. So now, next one. So let D be a subset of B. The inverse image of D, the inverse image of D is defined as, look at symbolism now. We now just read this as F inverse D. So that's a F with a negative one at the top. I don't like what I look. Right again. F inverse. Yeah. The first one, you couldn't see the negative one clearly. So F inverse D. So the inverse image of D is defined as this thing here, which is the set X in A, the set of X in A, such that F of X is in D. So to make it easier for you, Mikila, look at this. I'm going to underline the result. It's when you want to find a direct image, it is the Y values. You can think of it the way we normally use X and Y. It's the result you get after putting it in the function. Whereas the inverse image is the what you started with. It's from the domain. So simply put, direct image F of X, inverse image the original X. That's a simple way of looking at it. But if you want to be technical, the direct image are the results obtained in the codomain, assuming that the original element came from the domain, and the inverse image is the original results in the domain which provided the range. All right. But you have to be careful with the direct image. So the direct image, are the elements that you get in the range, not the codomain, because are not necessarily the codomain, because remember the range, the elements in the range are part of the codomain, but not everything in the codomain is in the range. So the direct image is the results in the range, specifically. All right. You know what? Let's do some quick examples to make sure it is clear. So let's say we have 1, 2, 3, and 4. And we're doing some mapping to A, B, C, and D. So let us say 1 maps to B, 2 maps to D, 4 maps to B, and 3 maps to C, straight across. All right. I'm going to write some, I'm going to write it exactly right here. The function mapping 1, 2, 3, and 4 results in A, B, C, and D. No, to specify directly, the direct image obtained from 1 is B. So that's a direct image obtained from 1. If I wanted to write the inverse image, that's a negative 1 at the top. The inverse image of ABC. I'll put this up next bracket out here. So the inverse image of the set ABC would be the set what? Let me see if you guys pick it up. What is the inverse image of the set ABC? We're going back to the domain now, you know. Guys, don't leave me hanging. What is the inverse image of the set ABC?
Sir. But A is not, nothing is mapped to A.
You know where about that.
All right.
Oh, so that's why you guys paused. All right, let me give you an easier one then. I'll come back to that one. What is the inverse image of the set? Let's use B. What's the inverse image of the set B?
1 and 4.
1 and 4. Because you can see B came from 1 and 4. All right. So let me make it easier for you then. What's the inverse image of the set A? Set containing A. You better can get this one right.
Oh, the empty set.
Empty set. Good. Got nothing mapping from A to nothing maps to A. So back to what I was saying up there. What's the inverse image of the set A, B, C? Come on, make me proud.
It include the empty set.
All right.
And B and 1, 4, 3. 1, 3, 4.
Correct. That's it. 1, 3, 4.
But wouldn't you put the empty set in it? Or that's oh yeah, never mind, because the empty set is part of every set.
Exactly. I was just about to say that, but since you mentioned it, there you go. And the set is a part of every set. So you don't have to write it separately. All right. So I can say that inverse image was the one that gave the most trouble. Well, that's about it. Yeah. I was going to write more direct images, but you don't need that. I think everybody knows direct images. For example, the direct image of 1, 2, 4 is just BD. Say 1, 2, and 4 maps to B and D only. So don't be fooled. If a set is not a part of the range, sorry, if an element is not a part of the range, and you want to find the inverse image of it, as Anthony mentioned a while ago, it's just an empty set. So like, for example, if you're looking at the function x squared, and you want to find the inverse image of -5, there will be none. Because once you square the number, you're not getting a negative result. All right. So that's image and direct image. I mean, image, direct image, same thing, and inverse image. Next definition. Ah, but you know what? Before I give the next definition, let me see if you guys understand this concept. Wait, hope you weren't writing, you know. If you're writing, sorry about that. You can just watch the recording again. Look at this. Let us use the mapping from real numbers to real numbers. And we want to, oh, by the way, you're going to see this mentioned each time now. This will let you know what the range is and what the codomain is each time. That's why when we're doing functions, like when you're looking at the function f of x squared, sorry, the function, yeah, f of x squared, you have to have a specific domain and range because, wait, you know what, let me not say anything yet because there's a question I want to ask you about it later. Let's see if you pick it up. All right, so let f be the mapping from real numbers to real numbers, and it's defined by f of x equals sine pi x. So doing some pre-calculus now. That's a x, sorry. Sine pi x. So here's my question now. If we're using this domain, the domain which is from 0 to a half, what is going to be the range? I mean, maybe a hint. It starts at 0. So if we're mapping from 0 to a half, what's the end result we're going to get? 0 to what? Using sine.
Is it the sine of a half? 0.5. Well, never mind. That'll make sense. That'll be sine of 30 is what?
I won't say anything until you tell me the number, because if I say anything, it's going to be a hint. I don't want to give any hints. This is just testing your pre-cal knowledge, but it's nothing, don't think too hard.
Sine of 0 is 0.
Well, trigonometry knowledge in general. No, not 30, Lafern.
You have to convert it. So you probably can put
No, it's not no conversion. Remember, when you find the sign of a number.
5 or 6. 5 or 6.
No, man. No. Oh, I think you miss. You don't remember what happens between 0 and a half. Remember, no, the 0 and a half, you know, is being multiplied by the pi. From the 0 to the half, you multiply by pi.
Oh, yeah, that's true. Okay. That's what? 90. So that'll be 1.
1. That is the answer. 0 to 1. You guys forgot the pi. 0
Well,
times pi is 0.
I was thinking of it wrong.
Yeah, I realized that's what I was telling you. Lafern was looking at the domain, not the range. That's why she said 30. All right, so if there's any confusion, let's clear it up. You're going from 0, because you know pi times 0 is 0. So it ranges from this, from the sine of 0 to the sine of pi times a half, which is just pi by 2.
And sine is sorry.
Sine is up?
And it's also that there's a range between -1 and 1, right?
Right, but since we limited it to 0 to half, we don't get the negatives there. That's why it just goes from 0 to 1. If we had said from 0 to 1 now, well, not even 0 to 1. But let's come back down to 0. If we had increased the range a little bit, the domain, sorry, a little bit, you have gotten to include the negative numbers in the domain. If you had included some more numbers in the domain, you'd have gotten the negative numbers to be included in the range. Right. But since we limited it from 0 to half, it doesn't go below 0. And of course, it can't go above 1. for the range. All right, everybody okay with that? So these little things gonna come back, you know, trigonometry and stuff. So make sure you remember them. Anyway, so I just wanted to see if you guys. When I was looking through the textbook, I saw that one. I said, you know, let's see if the guys pick up that it's 0 to 1. But anyway, oh, by the way, what is the? Should I ask you this? I'll ask it too. The same. If you're using the same function, let me underline it. If you're using this same function right here, think very critically now. If you're using that same function, what is the inverse image of 0 going to be? Think very carefully now. What's the inverse image of 0 using sine, you know? All right. Sorry, not using sine, using sine pi x. So what the question that we're trying to get now is what x is, oh, I'm giving it away. What is the inverse image of 0? Oh, this is probably one question that I can give bonus marks. Not just 0. Be more specific. I mean, give me some more. I'm specific about it. So 0 is correct, but it's not the only result.
Pi over 2.
No. Remember, the pi is already mentioned, you know. It's the x's that you want.
Okay.
I'll give you 1 minute to get a bonus mark.
Is it half?
I'll actually work it out for you when I'm finished. But I'm not telling you right now.
180.
No. You guys are forgetting, you know. See, actually underline the function sine pi x. The pi is already in there. The x is what I want. Whenever you get a question like this, and you ask to find the domain, or the inverse image really, you're looking for the x values. So forget, see the pi is already there. 1 is part of it, Laferne. Good. 0 is correct. 1 is correct. Keep going. 30 seconds left to get bonus marks. 30 seconds. 36.
-1.
Not this one more too. So what is the general answer? 10 seconds.
-1 to 1.
More than that. 5
Open
seconds.
bracket. -1,
More.
comma, +1.
More than that. 2.
Infinity.
Oh, okay. Time is up.
What is the answer?
All right. What is the sign of 2 pi?
What's the side of 2 pi? 2 pi is 360. Circle.
Yeah. What's the sign of it?
Oh, what's the sign of 2 pi?
All right. Let me start from 0. What's the sign of 0?
0.
What's the sign of pi? 1 pi, which is just pi.
That's +1, I think.
Remember the circle, you know, it goes up to 90. That's 1. Come back down to 180.
Stop on 0.
0. What's the sign of
What's
2
it?
pi?
2 pi. This is 0 to 180.
Remind you the thing. 0, right? See? This is 0 right here. I'm going to put all the zeros. Sign of 0 right here. Sign of 180 right here. Sign of 2 pi right here. Well, sorry, let me say it a different way. The first one is the sign of 0. Second one is the sign of 1 pi. Third one is the sign of 2 pi. Next one is the sign of what? Multiply that. No, 4 pi left.
3 pi.
Remember, we started at 0. 3 pi, yeah. Next one, when you come back up to 4 pi. Because it just keeps going up pi, 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 right at the zeros. If you go backward, if you started here instead and go backward, negative pi, negative 2 pi, negative 3 pi, and so forth. So, what is the inverse image of 0 in this case? Look at the numbers that I'm getting. So we got 0, 1, 2, 3, 4. I'll go count backward the other way. You got negative 1, negative 2, negative 3. A set of what? Oh, I thought I gave you the answer. No, I'm writing down. What?
Integers.
What is it? Correct. That's the answer. Lafern, I get it, you know. Hold on. Let me show you what I'm going. Hold on, Lafern. Hold on. Look at this. So you see when you ask, all right, this is the function we're using. Sine of pi x. That's our function, right? You see when you ask to find the inverse image, you ask to find the possible x values that fit into your inverse image. So in other words, you're given this question and asked to solve for x. That's what it does. That's what it does a while ago. You know? You're given sine pi x equals 0, and you ask to find the inverse image of 0. In other words, you have to go back and find the x that gives you that 0. I just told you them a while ago. If you put 1 in there, that's sine pi. If you put 2 in there, that's sine 2 pi. We're putting the x values in, you know, what you want to find is the values of x that make this thing 0. If you put negative 1 in there, that's negative pi. All of those integers give you, any integer you put in there for x, you're going to get 0 as a result. If you wanted to prove it the mathematical way, of course, you could, you know, take the sine inverse of 0, and you get 0, then you what do you call it? You transpose, you get x. But you have to remember this. Whenever you solve a sine equation, you do the inverse sine, the results are equal to pi x, pi x is equal, would have been equal to 0 plus or minus pi k. If you remember that. Of course, let me ask about if you remember that. You're supposed to know that from pre-calculus. Because for the sine, once you keep adding 180 to a sine, 180 to a term, to a number, the sine of it will be the same. For example, if I told the sine of something is, let's say the sine of y is let's say negative 3. A lot of mercy, I'm talking about negative 3. You can't get 3. Negative 0.2. Just for argument's sake. If I add 180 to that y, and you find the sine of it again, you're going to get the same result. Right? So whenever you have the sine of a number, and 180 is added to that number, 180 degrees, of course, or pi is added to it, the sine of it will be the same. Something you need to remember. Or something you should have remembered, I should say. Anyway, no time on that. That's pre-calculus. I should have really teaching pre-calculus. Although you should have used in calculus too. In cal, I wish calculus using again. I don't remember. Anyway, any questions? You understand it now? So the answer was all integers, because any integer you put in there, the sine of it will be 0. Sine of 2 pi is 0, sine of 3 pi is 0, sine of 4 pi is 0, sine of negative pi is 0, sine of negative 2 pi is 0. You get the point. All right. On to another definition type thing, but this is more like a theorem. So I need to write this down because to read it will be difficult. So write this down. This is a theorem or a proposition, or yeah, call it proposition. This is a proposition. Let f mapping A to B, remember I told that this is how it's written. Let f mapping A to B but in this case I needed to say it this way. Let f be a function mapping A to B because it's full stop right after that. All right. Full stop. And let C and D be subsets of B. So let C and D be subsets of B. Be subsets. I don't need to write that. You can write it. Let C and D be subsets of B. So they are subsets of the codomain. So let C and D be subsets of B, which is the codomain. All right, full stop. Then, so these are the to get to know. Then the inverse image of C union D is the inverse image of C union the inverse image of D. That's one. So that's inverse image of the union. So the inverse image, remember, C and D are in the codomain. You're not in the domain. That's why you can take the inverse image of them. So the inverse image of the intersection of the those two subsets, intersection should be an upside down thing. Sorry, is the inverse image of C intersected with the inverse image of D. So these are not hard to remember because they're very straightforward. They're not fancy like the De Morgan theorem. And finally, the inverse image of the complement of a subset in the domain is the inverse image, or I should say complement, of the inverse image of that subset. So if you take the inverse image of the subset, it's the same as just finding an inverse image and finding its complement. I could show some examples, but with a drawing. If I were at school, I'd just, or using a camera, I would do it. But to write on this board and do it, Lord of mercy, man. But I might show it to you. Oh, for the last line, and next week we write it. And this time it's not a general thing, it's the exact thing that's been said this time. And next week could have been written is like this. Because since A is the oh, you guys finish writing? I don't want to be talking when writing. I want to make sure you see it. Anyone still writing? All right. This next week could have written it. Since A is the domain, we're sure that A is the domain. Then we could write it like this. The inverse image of, oh, wait, let me not say anything. Do you guys remember how to read this? How do you read that thing I just wrote about in brackets? How do you read that? Does anybody remember how to read that? Let me start it off for you. The complement of C. That B stroke C thing, how is it read?
The complement of C relative to B.
Wonderful, Michaela. Thank you very much. Where was Michaela? I think so, because that's friend normally sounds a therapy. Thank you, Michaela. So that's a complement of C relative to B, which is the same as this. Which is a complement of the inverse image of C relative to A. So the inverse image of the complement of C relative to B, yeah.
What if it's a two set?
What if it's two set?
Yeah.
What do you mean for the complement?
No, what if it's a two set problem you're looking at? You don't have set A, you only have set A and B. Well, kind of hard to explain. What if you only have A set A and B?
Yeah, that's what the last two lines refer to only set A and B.
Right, but you wouldn't have C involved in it in that case. This is referring to if you have three sets. A, B, and C.
No man. I thought well, I thought you meant, oh, so you mean if it's just A and B only, no C and D business? That's what you're talking about? Andrew? I mean Anthony? Anthony?
Yes, sir. How would the formula look? If you don't have if it's a two set problem you're working with. Yeah, set A and B only.
All right, first let me explain to you why they use the three sets here. Let me show you why they use the A, B, and C. In most mathematical problems, you have a codomain, and out of that domain, you have the range. This problem here is assuming that the codomain and the range are not the same. That is why they have mentioned C, B, and A. So what you're asking is, what if you only have the domain and range? There's no, meaning the domain and the range, sorry, the codomain and the range are the same thing. That's what you're asking. In that case, then the complement would just be an empty set.
Oh, okay. All right. Gotcha.
All right. All right. Any other questions? How much time do we have left? Oh, we have enough time, man. Can keep going. Any other questions? No? Anyone still writing? No? Erasing. Next. Let F be a mapping from A to B. Yes, that's the way I can say it. So I can say full stop after that. So let F be a mapping from A to B. The same thing that I said before again. So this is another proposition. Let C and D be subsets of A this time. So a while ago, the C and D were subsets of the codomain. Now they're subsets of the domain. So let C and D be subsets of A. Then everything is nice and simple. The function of C union D is simply the function of C united with the function of D. And the same thing goes for the intersection. The function of the intersection of C and D is just the function of this. Whoops. The subset. Beg pardon. It's a subset of the function of C intersected with the function of D. So the function of the intersection of C and D is a subset of, so it can be equal, but it's usually just a part of the intersection of those two. All right, nice. We're almost finished functions now. Of course, you do questions later, but I just want to get through all the definitions and intersection. I mean, propositions and theorems. So we're right up to the last one now, which is to define types of functions. So there are three special types of functions. And there's a
Is that
yellow
equal the last line?
subset.
Oh.
It can be equal, but it doesn't have to be. That's why I make sure to put subset and not proper subset. All right, where was I going? Yes, types of functions. The first type, well, write this down, definition. Let f be a mapping from A to B. So let the function f be a mapping from A to B, set A to set B. So let the mapping from A to B be a function. Okay, you can have mappings, that are not functions. But generally, when you say the right f as the mapping, it's a function. I should have mentioned that. I could have said let P be a mapping from A to B. Or anything you want to map what. It could be G, P, Q, whatever. But generally, when you use f, it is a function. Generally. Don't take me as gospel as saying it's always a function. If it's a function, they will specify it as a function. Because there are different mappings, there are different relations, which you'll see later. It doesn't have to be a function. So anyway, write this down. Let f be a mapping from A to B be a function. Make sure you write those words. It must be a function. So write this now, full stop. The function, this is important now, I'm going to read it slowly. The function f is said to be injective. The function f is said to be injective. I'm pretty sure you saw that term before. I saw it in high school. But I didn't remember what it meant when I was at high school. All right, the function f is said to be injective or one-to-one. I'm going to write like this, 1-2-1. So it's said to be injective or one-to-one if f of x1, f of subscript 1 is equal to f of x subscript 2. So if f of subscript, that thing here, f of x1 is equal to f of x2 only if x1 equal x2. Now, the way they worded that might confuse you. I'm going to simplify it a bit. So the function f is said to be injective or one-to-one if f of x1 equals f of x2 only if x1 equals x2. So I'm going to put in my simpler words. Should have that full stop. I could put comma, meaning f is injective if you have no more than one element from B, sorry, no more than one element from A mapping to an element in B. If you have no more than one element in A mapping to an element in B. That's why they call it one-to-one. You can't have two going to one. You can have functions where you have two elements going to the same element. That's a function. Like in x squared, both 3 squared and negative 3 squared go to 9. So that's still a function. But for it to be injective, that can't happen. You can only have one element in A going to an element in B. No more than one. So that's what injective is. So let me just explain to you what they were saying right here when they have the this right here. That if f of x1 is equal to f of x2, it means that x1 is x2. That's what they're saying. If you see a situation where f of some x, let's say f of x was the same as f of 4, it meant that x must have been 4 because they couldn't have one element in x, one element in A go an element in B, and the next element in A going to the same element in B. They must have been the same element. That's what they're saying when they said if f of x1 equal f of x2, then x1 must have been x2. That's what they're saying, what I meant when I said that part right there. So that's another way of saying that if one element is going to, if one element in A is going to an element in B, and you seem to have a next element in A going to the same element in B, it means that the two of them must have been the same. Otherwise, it would not have been injective. Okay, moving on. Everybody understand that? Or let me ask a different way. Is there anyone who not quite so sure what that is saying? Okay, good. All right. Surjective. So let's look at what that is. The function f, so using the same mapping that we have up here. Same mapping for this definition. The function f is said to be surjective. The function f is said to be surjective. Oh, Make sure you spell that properly. It's not SIR, it's SUR. Surjective. That's I. It's said to be surjective or onto, O-N-T-O. Oh my, O-N-T-O, or onto. It's said to be surjective or onto if f of A equals f of B. Beg pardon, if f of A equal B. Oh boy. The set function f is said to be surjective if f of A equal B. So that means that maybe you guys know what it means already. Do you?
Go ahead, explain, sir.
Oh, okay.
I think
So,
I've never been taught injective, surjective, and those things. You know, I always wanted to look them up. So
well, I'll better then.
that's
You know,
great.
one time when this course was being taught, well, I shouldn't say one time, when I was being taught this course at UA, the guy just came and said, okay, you guys know these meanings already. And he went straight on to the next topic. I think we're supposed to learn it somewhere, but I don't remember where. But I think I learned them in high school, but not in the details I needed to know. So anyway, surjective means, so when I say f of A equals B, remember before, you know, if you have a mapping from A to B, right? Not everything in B has to be used. But if it is surjective, when I say f of A equals B, it means that everything in B was mapped to. So all elements in B were used. That's what surjective means. It means that there's nothing left out from B that wasn't used. So let me give you some quick examples. Make sure it is clear. 1, 2, 3. And let's say we have over here, we have A, B, C, D. So for injective, all right, let me just leave it surjective first. This would not be a surjective function because, as you can see, that D was not used. If we had something like this now, so that would not be surjective. Why? Because f was not equal to b. F of a was equal to ABC. In other words, all the elements from A mapped to A, B, and C from the B. So this is A over here, this is B over here. So f of A was not equal to B, f of A was equal to A, B, and C. But if we had something like this one now, 1, 2, 3, you don't even have that. Matter of fact, I'm going to put A and B alone over here. You have 1 going to A, 2 going to, and 3 going to B. This is surjective. Why is that so? Because everything in A, or let me say it a different way, everything in B had something mapping to it from A. That is surjective. So since you have these two examples on the board, so let me say that one more time. The first mapping on the left with A and B, so there's a demarcation right here. This mapping was not surjective. Why? Because the D was left out in the mapping. B was not the complete mapping from A. So D was left out. In the second one, it is surjective. Why? Because everything in B was used in the mapping. Now, let's go back and check injective. So injective, A would also, the first mapping injective. Why? Because everything in A mapped to only one thing in B. Follow me? Or let's set a different way. Probably the way I say it will get confused, you know. You don't have more than one element in A mapping to the same element in B. For it to be injective, if something being mapped to in B, or no more than one can come from A to map to B. So A is not surjective, but it was injective because it was 1 to 1, as you can see. 1 in A going to 1 in B. Whereas the second one was surjective because everything in B was used up, but it was not injective because it had 2 elements in A going to 1 element in B. Zero? Surjective or injective? Hello?
Yes, sir. So injective, you say is 1 to 1.
Yeah.
And
But you can
surjective,
leave out surjective, huh?
can surjective be one-to-one as well too?
Yes, man.
Okay. So you can't really label them based on the relationship.
No. You see, as a matter of fact, the question you asked earlier, you asked me if surjective can be injective. Yes, and there's a name for that. So write this down. Well, I'm not. You finish writing? So remember, the left one is injective, the right one is surjective. The left one is not surjective, it is not injective. So last thing now. Function f that is both an injection. Well, that sounds weird. I think I prefer to word it this way. Unless you write it already. A function f that is both injective and surjective. I don't like call it using the word injection. I think it's something else. A function f that is both injective and surjective is said to be gay. Oh, sorry. It's said to be bijective. So if it has both the injection and the surjection, it is bijective. Right? So you know, bi means two. So it is said to be bijective. And F is said to be a bijection. So function F that is both injective and surjective, meaning it has both an injection and a surjection, is said to be bijective. And F is a bijection. All right. So let me show you a quick example of something that is both injective and surjective. A 1, 2, 3, 4. So if something is a bijection, it means that the number of elements, well, this is not a rule, but I've come to realize that it must be so. The number of elements in A must be the same as the number of elements in B. There's no other way it can be bijective. Because first of all, everything in B must be used up. And secondly, only one from A can go to B. So it must have the same. There must be a rule like that somewhere, but I don't see it. So that is a bijection. Because everything in A mapped to only one element in B. If it was injective, it was 1 to 1. And everything in B had something mapping to it from A. So it was a surd. So because it has both an injection and a surjection, it is a bijection. I like saying those words. Injection, surjection, bijection.
All right, sir. So let me just repeat what I understand what you're saying. You're saying everything in A, once everything in A is mapped to something in B, it's called an injection.
Me never said that, sir. I said when only one element from A, or let me say it a different way. When
Every
the
element
element in B
okay.
has only one element in A mapping to it, then it's an injection. Remember, you know, not all of them have to be used. That's why it's the best way to say it is no more than, for the elements in B, no more than one element in A is mapping to it.
Okay, so what if you have what if you have 5 in A and it's not mapped to any? Would that be an injection?
It wouldn't be a function. For it to be a function, everything in the domain has to map to something in B, in the codomain.
Okay.
Right. Let me just make sure. You asked me if there's something in A that's not mapping to anything, right? That's what you asked?
Yeah, I asked if you had like 5, the element 5 in A.
And it wasn't mapping to anything.
Yeah, so you said that's not a function.
Right?
Okay.
So for it to be a function, you can't have any domain element left out. It has to map to something. so continue with what you were asking. You're asking for what you think, what you understand it to be, or you're finished?
Okay, so the injection is that
Uh-huh.
every element in B
Mhm.
must be mapped from one and only one element in A.
Well, I wouldn't say it must be mapped, but every element in B must have no more than one mapping to it from A. So you can have none, you know. Like if I so right now the one that I have on the board is a surjection and injection. But if I were to increase it by putting an extra element right here, let's say E, it would still be an injection because each of the elements in B had only one element from A mapping to it. See? A had only two, B had only one, C had only three. I said only three and only one, I mean the elements in A. And only the four was mapping to the D. Even though there's nothing mapping to the E, it is still an injection because no more than one element from A was mapping to an element in B. So the injection doesn't require that everything is mapped to, you know. It just requires that each of the elements that have something mapping to it is only one element coming to it, no more than one. So that is an injection.
Okay, got you.
So even though they say injection is one-to-one, I think the better way to look at it is no more than one going to B, to each element in B. But they call it one-to-one because, as you can see, one in A going to one in B, even though some of them have nothing going to it. So the one I have on the board is an injection. Since I increase it, I put the E on it, it is still an injection because no more than one from A was going to something in B. But this is no longer a surjection because now the E doesn't have anything mapping to it. And for it to be a surjection or to be surjective, everything in B must have something mapping to it from A. That's clear now?
Right. So can I think of injection from A standpoint by saying each element in A must be mapped to own. Well, no, that can't work. That can't work. All right, I'll stick to
I
what
know
you
what
said.
you're going to say. You're going to say, yeah, but that is what you're defining is a function. Because if you
Yes.
were to have one element in A going to two elements in B, it would no longer be a function. Like one going to A and one going to B, not a function. That's what you call many to one.
You mean one to many?
One to many, sorry, yes, one to many.
Yeah. So I said. So you always have to think from the standpoint of B for both injection
Right.
and
Correct.
surjection.
Yes. Codomy is the important part, or the range. All right, so we're a bit over time, so let me start recording here. And Laffer